In part 1 and 2, we discussed the requirements for this project and the hardware-software components used. In part 3, we will take a high-level view of the system that we will build as part of this workshop. I will also discuss some design choices we made and why we made them. Let me start with a high-level block diagram of the system. In this diagram, I want to emphasize that we are collecting data using multiple Raspberry Pis, possibly connected to the internet using various Wi-Fi access points. Each Raspberry Pi can collect data on more than one plant. Each plant, or a whole bed of plants, can have multiple sensors and actuators deployed. We will call the Raspberry Pis the servers. 0 or more clients can connect to these Pis at any given time. The data is stored locally in each of the Pis. The servers and clients can be geographically distributed with a network delay. The communication or interface between the clients and servers is abstracted using the gRPC protocol. gRPC is a relatively recent remote procedure call system. An alternative to gRPC that is more popular on the internet currently uses REST, which stands for Representational State Transfer. Both REST and gRPC are reasonably similar. I will explain in a little bit why we chose gRPC, but the decision is probably not systemic. That is, we could have chosen either one and the system would have worked. Let us see another alternative architecture. In this architecture, we add a backend in the cloud. Both the data sources, that is sensors, and data consumers, client frontends, connect to this backend. This architecture is prevalent in contemporary designs because of the availability of cloud as a service and many different cloud software offerings that one can use to build distributed systems, almost as if connecting Lego pieces. You must have heard of AWS, Google Cloud, and other popular offerings. For example, many Alexa-connected devices or home doorbell sensors, etc. will not work if the underlying cloud service goes offline. In that way, the cloud services are almost like a utility on top of the internet. I chose not to use this architecture because it is not necessary for this problem. That way, we simplify the system and do not commit ourselves to a recurring cost of this utility. If you think about it a little more, you can see why this architecture is prevalent though. It allows for data to be backed up continuously, and it is possible to scale the system such that the data can be processed and consumed by millions or even billions of users at a time. For example, if we had an application to display the number of COVID patients on a world map, we would expect that millions of people would access the data at any given time. We do not want to burden the data sources themselves to store and serve that data. However, we are talking about a private garden here. Even if all my cousins and best friends want to see what's happening with my garden, I would probably expect only about 10 users to view this data simultaneously. I have to admit, I don't have that many best friends, though I have a lot of friends on Facebook. I'm sure most of them would not find it entertaining to watch whether my orchid is getting the optimum amount of light and water. Okay, let me introduce you to the concept of a morphological matrix. The morph matrix is a tool to express and list the design choices available in a systematic way. At a high level, let's say we were considering these design choices I just discussed. We could consider all 4 options and discuss their merits based on the different relevant figures of merit dimensions like cost, ease of implementation, learning potential, etc. It is typical in an engineering project to have many more design variables. Still, At the same time, it isn't easy even for experienced engineering teams to think about them all at once. Hence, it makes sense to discuss a handful of design variables at a time. Just a reminder, this is the high-level architecture that I chose for this system. Here are some of the considerations that I took into account in choosing this architecture. 1. No cloud computing cost. 2. Faster or more compressed data transfer, which was more important for another project where sensor data was being produced at 50 data points per second from several sensors. For monitoring plants, a slower data rate of perhaps 1 data point per second could be more practical, but we would still want to monitor many plants, and we'd want the data over many days or months or even years and transfer this data to the client when requested. So there is going to be a lot of data. 3. Interface definition files that produce code. I will talk about this in a subsequent section. 4. There was also a learning component, as gRPC is an up-and-coming technology and I wanted to get my hands wet on it. For part 4, we will move to the interface definition and server architecture. See you there.